hi guys, this is a calculus video and it's going to be video 7-1, but first, this is our green packet. Let's change unit 6 video packet to unit 7 video packet. Okay, so, and we're going to follow this calendar very, very closely. Okay, so as I am making this, it is Thursday. All right, so we're going to start off behind, but the first couple videos should not be hard to catch up on. Okay, so this video is to be watched. It's to be watched, we'll just say Thursday. Thursday, 2/23. And I'm not going to assign any homework with it. So the first problem is to evaluate the integral below using a calculator. Just a second. Okay, I just wanted to turn that light off. So, without a calculator, so it's a piecewise function, and the way that you have to evaluate an integral of a piecewise function is you have to split it up over the various intervals. So, the original integral is from 0 to 9, but we have to split up 0 to 9 from 0 to 2, and then from 2 to 5, and then from 5 to 9. So, it's going to be the integral from 0 to 2 of x squared dx plus the integral from 2 to 5 of 4 plus the integral from 5 to 9 of 9 minus x. Okay, and so the input in the integral is the part of the function that's defined on the interval that I'm integrating over. So this said without a calculator, so we've got to use the fundamental theorem. Okay, so I'm going to set this up. This is the fundamental theorem of calculus. The fundamental theorem of calculus relates area under curves to antiderivatives. All right, so if I want to find the area under the curve of x squared on the interval 0 to 2, I take the antiderivative of x squared. I go 1/3 x to the third. Nobody knew that finding area under a curve and antiderivatives were related until the fundamental theorem of calculus. So this is how it works. And then this one here, the antiderivative of 4 is 4x. Right, so the antiderivatives are going inside of the brackets. And then 9x minus 1/2 x squared. Okay? And then you plug in the endpoints and subtract. So I plug in 2, and I get 8/3 minus, and then what I get when I plug in 0. And they bring down the plus sign. Plug in 5, 20, minus what you get when you plug in 2. So 8. Bring down that plus sign. Plug in 9, and you get 81 minus 81/2 minus what you get when you plug in 5. So 45 minus 25/2. All right, and then I did this earlier, and when I simplified everything, this is what I got. All right, so over here, I'll just move over here. And I'm just going to we're getting ready for the AP test, so I'm going to, whoopsie, be very careful with my presentation. So I'll say, therefore, the integral from 0 to 9 of f of x is equal to, I got 68/3. Okay. Alrighty, so now this one, example 2, we're not going to do all these examples, but I'm tying up some loose ends, as I say in the title of this. If you see an integral and then it looks like there's nothing inside, that's actually a 1 inside. Alright, so let's do this example. So you put, if it's just an empty, like nothing inside the integral, it's just a 1 on the inside. Antiderivative of 1 is r, because this dr tells me that this is in terms of r. And then you plug in -10, and then minus, plug in 25. Okay, let's skip the next one. Alrighty, now here's another loose end. If you want to take the integral of an absolute value function, you go like this. So you take what's inside the absolute value. Okay, so I'm just take x. And then I set it equal to 0, we're going to do a sign test. But this has nothing to do with derivatives, okay? This is just a sign test to see where x is positive or negative. So I set it equal to 0, it's 0 at 0. To the left of 0, x is negative. To the right of 0, x is positive. So this means that you can express the absolute value of x as negative x when x is less than 0, and positive x when x is greater than or equal to 0. You just as easily could have said less than or equal here, and then this would have been just greater than. You just can't have, you know, both of them be 0, because then it wouldn't be we'd be using an x value twice. Okay. So, all right, and let's talk about in class, guys, why this is. All right, try to think for yourself why I was able to do this, and then I'll ask everyone at the beginning of class if someone could explain that to us. And okay, so I can rewrite this integral as the integral from -4 to 0 of this part, negative x, plus the integral from 0 to 10 of that part, x dx. Alrighty, now I'm going to save time and just to give you the answer, guys, but so the answer is 58, but you would get it the same way that we got this, okay, using the fundamental theorem of calculus and then plugging in the endpoints. Okay, let's skip this one. Okay, you can do that on your own if you want. We'll move right to a harder one to save time. Okay, so if you're taking the integral of an absolute value function, what you do is you take what's inside the absolute values and you set it equal to 0. You've got to do a sign test because you've got to figure out where, on what intervals this input is positive or negative. So I'm solving down here. All right, so on my number line, this is 0 when x is 0, and it's also 0 when x is 1. Just like the derivative sign test, but you're not taking the derivative at all. Okay, on this interval, this thing is negative, and then it's positive, and then it's negative. So that means that I can take the input of the integral and I can express it in 3 parts because I had 3 separate intervals here. I could express it, since it's negative on this interval, if I just negate what's inside, I would get positive. So the absolute value of this is, it's positive value. So if the inside is negative and I negate it, then it's positive. So I can express on this interval as, I kind of just explained what I said I was going to ask someone else too, but okay, for x is less than 0. And then on this interval, the input is positive anyway, so the whole thing is just positive without me changing it. Okay, for 0 less than or equal to x less than or equal to 1. Or you could put the less than or equals wherever you want, but you just can't have them in more than one spot. And then the last one was a negative interval, so if I negate it, it'd be positive. And then for x is greater than 1. Okay, so I'm going to split the integral up into 3 parts. So this is from -1 to 0, the first piece of the piecewise function that I wrote, plus from from 0. From 0 to 1, the positive, the not negated second piece, plus from 1 to 2. And then that's a negative interval again, so like that. And then you would do like, the brackets on it, you could do it just like this if it said no calculator. But just to say, okay, I'm going to do it. You can stop the video now if you want. All right, this wasn't that long of a video, so I'm going to keep going in case people who are uncomfortable with antiderivative or with integrals by hand, you can keep watching. But if you don't want to, you don't have to write anything past here. But stay with me if you feel uncomfortable with doing this. So I'm going to set up brackets like this underneath each integral. And then what goes inside of the brackets is the antiderivative of the integral's input. So this is going to be negative 1/2 x squared plus 1/3 x to the third. And then this, the antiderivative of this input is 1/2 x squared minus 1/3 x to the third. And then this one here, negative 1/2 x squared plus 1/3 x to the third. Okay, and then, so this is like an intermediate step. Now I'm going to get my answer using the fundamental theorem of calculus. This the whole process is the fundamental theorem, but this is going to be the result of it. So if I plug in 0, I get 0. Minus, when we plug in 1, we get negative 1/2 minus 1/3. And then I bring down that plus sign. When I plug in 1, I get 1/2 minus 1/3 minus, when I plug in 0, I get 0. Bring down that plus sign. When we plug in 2, we get negative 2 plus 8/3 minus, when we plug in 1, we get negative 1/2 plus 1/3. And then when you do all of that, so I'll say, therefore, the integral from negative 1 to 2, and you don't have to present it like this, guys. It's just, oopsie, sorry. It's just nice for your reader to be able to see your answer and your logic well. Alrighty. So there's that, guys, and I will see you soon. Bye-bye.